In this lesson, we're going to explore sampling distributions for means. Remember, a mean is used to summarize quantitative data, not categorical. I'm going to recap the central limit theorem that was beautifully explained by the AP Stat Guy. It states that if we draw a simple random sample of size n from any population with mean and a finite standard deviation, the central limit says that when n is large, the sampling distribution of the sample mean is approximately normal. And this is being illustrated in this picture. So here's your population, and you can see that it's bimodal, okay? But if we took the mean of this, it's probably going to be somewhere around right in here. And if we drew one particular sample and found the mean, so we took a couple, maybe of size 20, we found the mean of that and we plotted it over here, and we took another sample of size 20, found the mean and plotted it, and we kept doing this over and over, it would make a sampling distribution. And what we would find is the mean right here, mu, all the means of our individual samples to create this sampling distribution are going to stack up around the true mean of the population distribution, okay? Which is going to help us in a lot of scenarios here. So here are your formulas that we're going to encounter. So we expect, again, that the mean of our sampling distribution, that's what this is saying, the mean of all of our sample means, is equal to the true population mean. Now, to find the standard deviation of our sampling distribution, we take our population standard deviation and divide it by the square root of n. And hopefully you can see just algebraically that as n would get bigger, our standard deviation would get smaller. So as n increases our sample size, the variation will decrease. All right, so let's talk about our conditions for sampling distributions with means in order for it to be approximately normal. Our first one is random. Our sample has to be random without bias. These first two are really for independence. So it's the second one is the 10% condition. The sample size must be less than 10% of the population. And our third condition is the large counts condition. With proportions, it was we needed or expected at least 10 successes and at least 10 failures. But when we're talking about means, we don't have, a probability or a proportion to work with. So we need to consider two things. First of all, if we are making or drawing our samples from a population that's known to be normal, then our normality condition, or you call it your large counts, it's satisfied, okay? We don't have to consider it. We just state our population is normal, so the sample that we are drawing from it, we would expect to be normal as well. And the size then of your sample would not matter if that's the case. It can be really small, it can be big. However, if we have a population that's known to be non-normal, so it's skewed to the left, it's skewed to the right, it's symmetric, but it's not normal, we need to have a big enough sample size for the central limit theorem to kick in. So as long as our sample is greater than or equal to 30, we can assume that the sampling distribution of x bar is approximately normal. So when n is greater than or equal to 30, the sampling distribution of x bar is approximately normal by the central limit theorem. So in our first example, a college phys ed department asked a random sample of 200 female students to self-report their heights and weights. But the percentage of students with body mass indexes over 25 seemed suspiciously low. One possible explanation may be that the respondents shaded their weights down a bit. Like, maybe they exaggerated and said they weren't weighing as much as they, really did. The CDC reports that the mean weight of 18-year-old women is 143.74 pounds, with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of 140 pounds. Based on the central limit theorem and the 68-95-99.7 rule, does the mean weight in this sample seem exceptionally low, or might this just be random sample to sample variation? Okay, so is there something shady happening here? Are these young ladies exaggerating their weights, or is this natural variation due to chance? In order to really look at this and use our normal model, we need to check our conditions for means. First of all, it's random. It states that 200 females were randomly sampled. So I'm doing a little bit of assuming with the 10% condition, but I'm going to state that 200 females is less than 10% of women at the college. And next I'm going to check my large counts or normality condition. Because the sample size equals 200 is greater than or equal to 30 by the central limit theorem, we know that the distribution of X bar is approximately normal. So it is okay to proceed with a normal model to describe the distribution of the mean weights of respondents. So now, since I'm using a normal model, I'm going to need my mean and standard deviation. So I need my mean. So mu of X bar, you can pull it off your formula sheet. We would expect it to be equal to the true mean, which we are using, this is kind of in theory land. The CDC says it's 143.74 pounds. And then we need our standard deviation of our sampling distribution. Okay, so this would be the distribution of all samples of size 200, what that standard deviation is. So that's equal to the population standard deviation divided by the square root of our sample size. So we are told that that's 51.54 divided by the square root of 200, and I get approximately 3.64. Okay, so I have my model with my parameters clearly defined and I show where I got those numbers. Okay, so I'm supposed to show by the 68, 95, 97 rule whether or not our particular observed sample is unusual. So our observed sample mean is 140 is what this group reported, of having a mean of 140 pounds. So I'm going to sketch a normal model. So off on the side, I just made my normal model, and now I'm going to include my 68, 95, 97 rule. I'm just going to illustrate that I understand what that means. So within 3 standard deviations of the mean, I've got 99.7% of my data. Within 2 standard deviations of the mean, I've got 95% of my data. And within 1 standard deviation on either side, that is 68% of my data. Okay, so trying to line this up with my tick marks. Okay. And now, as I look at this, 140 is going to be about right here. So is that exceptionally low? Well, to really talk about it, I'm going to quickly find my z-score. So my z-score is equal to my observed mean minus the mean of the sampling distribution divided by the standard deviation of the sampling distribution. So 140 minus 143.74 divided by 3.64 gives me negative 1.027. So a little more than 1 standard deviation below the mean. So definitely not exceptionally low. So the mean of 140 pounds is not exceptionally low. It is only a little more than 1 standard deviation below the mean. So by the 68, 95, 99, 7 rule, only about 16% are going to be below 1 standard deviation below the mean, because 68% is within 1%, so 100 minus 68% is a remaining 34%, so, or excuse me, 32%. That puts 16% on either side. So I'm saying 16% of, now I'm talking about what this sampling distribution is, of samples of size, always state the size, of size 200 will have a mean at or lower than 140 pounds because it would be that or more extreme. In example 2 here, we're going to look at the difference between finding a probability for one young woman or the probability of finding an entire group of women. Okay, so part A, well, let's read the backstory. The heights of young women follow a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. So find the probability that a randomly selected young woman, so this is just one young woman, is taller than 66.5 inches. Okay, so to do this, let's go to our normal model. We're told it follows a normal distribution, okay, and we are given our mean 64.5 and our standard deviation of 2.5, so sketch it. So I sketched my normal model, and what it's asking us, what is the probability, so we're looking within our population, of taking one young woman who has a height greater than 66.5. So I'm going to label this 66.5 is going to be about right here, and I'm going to shade this in to find this probability. Now, I got two options here. I could find my z-score, or I can do a little calculator talk here, as long as make sure you have this statement here is equal to normal CDF, and you're going to label your lower 66.5 for 9999 and mu and sigma, and I put that in and I get 0.2119. So there's about a 21% chance that a randomly selected woman, so just one, is taller than 66.5 inches. So now we're going to look at finding a group of 10 young women. So we're going to find the probability that the mean height of a simple random sample of any 10 young women is greater than 66.5. So think about what's more unusual. Is it more unusual to find one woman who's taller than 66.5, or take an entire group of women, find their average heights, and have that greater than 66.5? I hope you realize that it's more unusual to find that entire group. Could we have one or two women, but an entire group? That's going to be unusual. So again, that's what this one here is stating. So to find that entire group of young women, now we're going to a sampling distribution, and we need to know if this is approximately normal. So you need to address your three conditions. So I have my three conditions. First of all, random. An SRS of 10 young women was selected. 10% condition, the sample of 10 young women make up less than 10% of, not off, of the population of all women. And then the large counts condition. Well, I'm hoping it jumped out at you that this is not greater than or equal to 30 for our size of our sample. But it was drawn from a normal population. So the sample is drawn from a normal population, so the distribution of our sample means is also normal. So our sampling distribution is approximately normal, and I am going to use, I know it's equal to the population mean, which from previous problem or at the top of your paper is 64.5, and the standard deviation of my sample distribution is equal to, my sampling distribution I meant to say, is equal to the true standard deviation, which we were told was 2.5 divided by square root of my sample size, so square root of 10, I get 0.7906, so I'm going to sketch a normal model. So you'll also notice that hopefully that your standard deviation here, 0.7906, is much smaller than when we looked at our population standard deviation. Okay, so every individual graph had a standard deviation of 2.5. When we take samples of size 10 and we infinitely generate them, our standard deviation here is 0.7906, so it's smaller. Okay, so we are asked, what is the probability? So not that an individual person, not an X, but the mean, the sample mean, is greater than 66.5. So if you are prone to find your z-scores, I'm going to put that in here, greater than 2.53. You could use table A. You can do normal CDF. And when I do that, I get 0.0057. So much smaller chance of this occurring. So there is approximately 0.57% chance, so less than 1%, whereas before we had nearly 21% chance of getting one woman from your population. But less than 1% chance of selecting a sample of 10 women whose mean height exceeds 66.5 inches.